Hello, everybody. My name is Elisa Baum, and I am Percona's Director of Product Marketing. We'll begin in just a moment, but first I'd like to conduct just a bit of house cleaning. Would you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know that you can hear me? Okay, I see lots of hands. Thank you, everybody. Next, during this webinar, you will be on mute. Should you have any questions at all during the discussion, please enter them in the questions field within the GoToWebinar control panel. At the end of the webinar, we will take time to answer as many questions as possible, and those that aren't addressed will be answered in a follow-up blog entry on Percona's MySQL performance blog, and perhaps via personal email from the speakers as well. In addition, a recording of this webinar will be made available to everybody within 48 hours. So with that said, I'd like to thank you for today's very special webinar, How to Optimally Configure Sphinx Search for MySQL. This is being jointly presented today by Percona Principal Consultant Ryan Lowe and our very special guest star, Andrew Aksonoff, CEO and CTO of Sphinx Search. With that said, I'd like to turn the floor over to Ryan to begin. Ryan, go ahead.
All right, can you hear me?
I can hear you.
Fantastic. So hi everybody, my name is Ryan. Again, I'm a consultant at Percona, and with me is Andrew, the CEO and founder and CTO of Sphinx. And we're here today to talk to you about using Sphinx with MySQL, the similarities and differences between using Sphinx for full-text searching versus MySQL's full-text searching using my eyes MerinoDB, and generally provide a high-level overview of Sphinx's capabilities. I tried to merge the MySQL and Sphinx logos here to show how they can work together seamlessly, but my Photoshop skills are kind of terrible. You'll see a few of these gems in this presentation today. The target for this presentation is somewhat unique. There are a whole host of presentations out there for how to start using Sphinx in 3 commands, and it's actually incredibly simple. Additionally, there are advanced tutorials for how to scale Sphinx to handle billions of searches a second, which also turns out to be surprisingly easy. But we're trying to target here a group somewhere in the middle. We expect that you should be able to use Sphinx but are trying to get more out of it, or you're trying to evaluate full-text search products and their relevance in light of the ability to use full-text indexes with MerinoDB starting in MySQL 5.6. So we're going to try to leave a lot of time for questions at the end, so please ask away during the presentation. And as Alyssa said, we'll be doing at least one follow-up blog post to try to answer the questions that we miss, or the ones that are too complicated to answer in the webinar format. So a quick overview of today's schedule. We'll start by defining full-text search and why we care, and this is mostly just to make sure that everybody's on the same page. It'll be rather quick. Then we'll talk about features and functionality that are different between MySQL and Sphinx, specifically the nuances, scaling, and search results quality. And finally, we'll end by talking about how MySQL and Sphinx are often used together in the stack, ending up as complementary technologies rather than competing ones. So what is full-text search? According to Wikipedia, full-text search is a technique for searching a collection of documents where each word in every document is matched against the search criteria. And here the term document can literally mean a file on a disk, a row in a database, an I/O stream, or any other form where text can be read and processed. Seems simple, right? Well, there's a lot more to it than that. Back in the day, having a distributed version of grep would have meant that you had the most powerful full-text search solution around. But that's not the case anymore. The world of search has become much more nuanced. And the increased complexity of full-text search over the years has come from a handful of very awesome components, and we'll talk about each of these by themselves and try to give both examples in MySQL and Sphinx. We'll start by talking about ranking and relevance, stemming and morphology, keyword expansion, punctuation and delimiters, and then character sets. So document ranking and ranking algorithms in general really became a matter of public concern when Google began talking publicly about their PageRank algorithm. And although we now know that Google takes into account a number of factors other than textual relevance, such as page load time, how long a domain's been active, link backs, and whatnot, we also know that textual analysis plays a significant component. So simply put, ranking full-text search results is computing a relevance value or a weight for a given document. And there are more ways to compute ranking than I can count, and that's not just because I can't count very high. There are actually a lot of approaches. Sadly, rank and relevance are ultimately subjective. What's completely relevant to you may be totally irrelevant to me. Consider Sinatra. There are a whole host of documents out there about Sinatra, but while you may be looking for Old Blue Eyes, I might be looking for technical documentation about the domain-specific language for building web applications in Ruby. Ranking is hard. At my last count, there were 8 ways that Sphinx could rank results, and these are divided roughly into 3 categories. First are the simple rankers. None does nothing, as the name implies. Word count simply counts keyword occurrences, and field mask returns the matching field's bit mask. These 3 ranking systems are appropriate for when ranking's not needed at all, or when ranking is computed on the application side. And a good example of this is when you want to get a list of products but then order them by price or something non-full text related. Next are the legacy rankers, which rely on phrase proximity alone and emulate all and any matching modes respectively. And finally, the advanced rankers are where most of you should really be looking. Because they're more advanced, they also tend to be both more I/O intensive and computationally intensive than the other methods of ranking. And at the bottom of the page, I put one of the most prominent instantiations of BM25 because it's really the foundation of all the advanced ranking methods. BM25 ranks documents based on the query terms appearing in each document, regardless of the relative proximity between the query terms within the document. It is considered to be state-of-the-art in document retrieval functions. Proximity BM25 is a simple improvement on BM25 in that user weights are multiplied by per field phrase proximities, and this is the default method of ranking in Sphinx. And then SPH04 improves on proximity BM25 by increasing the weight of matches that occur in the beginning of the document and ranking exact matches the highest, which is often useful. And I mentioned in the previous slide that ranking complexity does have an impact on performance, so we threw together a quick benchmark on the rankers, and this is what we got. Performing no ranking was obviously the fastest, taking less than 120 milliseconds, and a close second was BM25, and then everything else jumped into the 170 millisecond range. And while this sort of difference is normal between the easy versus hard ranking methods, the performance spread of the hard methods will vary considerably depending on the complexity of your searches, the size of the documents, and the volume of the documents being searched. So while the general consensus is that proximity BM25 and SPH04 provide the best ranking, the performance needs of your application should be evaluated in this context as well. And I'll now hand the presentation over to Andrew to talk in a bit more depth about ranking.
Right. Thanks, Ryan. So now to the advanced ranking, or as we, the search engine developers call it, ranking, because all the previous methods were rather simplistic, actually. I mean, they are the built-in formulas, the built-in ranking formulas, which date a while ago too, actually. I think proximity BM25 is as old as, say, 6 or maybe even 10 years old now. And these days you can and sometimes have to do much better than that. So proximity BM25 is in our current version of ICE, if you will, a simple formula which only combines the 2 ranking signals, the LCS factor, or as we call it consistently throughout the documentation, or a ranking signal, which, as they call it in the IR literature. So LCS is signal number 1, and BM25, that crazy formula that you saw on the slide just before, is the signal number 2, and we simply multiply the LCS by 1000 at BM25, sum it over all the fields, that's it. However, Sphinx now supports the the ranking formula number 9, if you will, which lets you specify an arbitrary mathematical expression and build your very own ranking formula out of a little plethora of all the ranking factors. I think right now we are counting 24 of different text-based factors, and then again you can of course throw in an arbitrary amount of pure document factors that you compute outside of Sphinx. So a simple example that you do not want to use is on the slide, filed under more complicated. To reiterate, you do not want to use that because that's something I, just made up the last evening. It does, however, show how you can use a bunch of plain factors like W, LCCS, and ATC, and mean gaps, and other esoteric variables, if you will, and also compute a more advanced version of BM25 with tweakable coefficients and Tor field weights and whatnot, plug that all into your ranking formula on the fly, and well, do some more advanced ranking than any of the built-in rankers provide. And this is actually useful. Even for the few million document collections, this is actually useful because some of the searches would end up fetching thousands and tens of thousands of results even in those collections, and Proximity BM25 does not always do a great job on that. It's really tough to build a general a silver bullet type of a generic ranker. I'm currently of a mind that every single vertical basically cries for its own customized ranker, and we do not yet have a ready-made built-in solution for every single vertical out there. We do, however, expose a mechanism to build your own. And finally, if you want to get really fancy about your ranking and build something web scale, really, as in searching through billions of documents and ranking them, well, pretty much the way the major web search engines do rank them, we also expose all the ranking factors that we compute to your UDFs, to your user-defined functions written in C or C++, and you can pass all that data to a super complicated function written to a super complicated UDF, and the point here is to be able to write really complicated functions that our built-in expression engine couldn't really handle. Well, think about a ranking function which is built out of 1,000 trees, of 1,000 different machine-learned decision trees. You can't really put that into the expression because most likely the query parser would blow. So that's it regarding the advanced ranking formulas. Next slide, please. And now, because little of the previous chatter made sense, a quick recap in plain English. So we've got lots of room for ranking tuning. We've got 24 signals right now, and that's 24 text signals, and we're constantly adding more. Some of those factors are pretty fast to compute. Some of them are slow, specifically the ATC and mean gaps factors that we've just added are particularly slow to compute. So normally, if you're using, in most cases, if you're either using them or if you're using the packet factors UDF interface, we have to compute all of them, including the most complicated ones. However, if you're using the expression ranker, we optimize for that and skip the computations of the heaviest 2 or 3 signals. And why does all that matter? Because, well, it gives you much slower search times, and by much slower I mean anywhere between 2 times and 10 times and sometimes even 100 times slower. But at the same time you get much better search quality this way. You can actually squeeze as good search quality as your typical run-of-the-mill web scale search engine would do, and I'm thinking Google, Yahoo, Bing, and whatnot here. So it might be overkill for 1 million documents. Again, I'm of the mind that going with the machine-learned functions with hundreds of signals is definitely overkill for just 1 million documents. However, a simple custom expression is a really good idea even for the smaller collections. And the super complicated expressions that Sphinx lets you plug in via the UDFs, they really are vital for the huge collections scaling to billions of documents. And that's it. Next.
Sure. So next
presenter,
I'll talk about.
I guess. Yeah. Next slide and next presenter.
Yeah. So we're going to talk about stemming next, but as you can tell, the ranking is sort of at the core of all that's interesting about full-text search. It's certainly one of the most popular topics, and an in-depth discussion of rankers and ranking in Sphinx can easily take run into the hours. So look at the Percona Live conference in what is it, April or May for some more in-depth discussion on Sphinx ranking. But stemming, let's move on. Stemming means to not index each word as it appears after lexing, but rather transforming it into its morphological root and indexing that instead. And two obvious examples of that are here. The words run, running, ran, runs, runner, and runnable can all be indexed as run. Similarly, compute, computer, computation, computers, computed, and computing all share the similar root of compute. And it's trivial to think of 1,000 more examples like this. The problem, though, is that it's also easy to think of 1,000 exceptions and then exceptions to those exceptions. Generally speaking, stemming is a difficult problem to solve, and even today in 2013, there are still a lot of mistakes in words that should be stemmed together but aren't, and even worse, words that should not be stemmed together but are. And Andrew will go into a little bit more detail.
Okay, it took me a little while to unmute myself again. So these are the examples, the specific examples from which the stemming approach, well, suffers. Because what stemming is basically is the reduction of the suffixes, or in plain English again, we take a word form like runner or running or runs or whatever. We look at that word form and we cut off a few last characters, or perhaps we replace those few last characters with a different one to arrive at a reasonably looking normal form of that word. However, it does come with, well, quite a bunch of mistakes. So depending on the context, even runner and walker might be a mistake. Even stemming those to the original word, to the original verb might be an issue. Think, for instance, about walker being used as a surname. That walker you definitely don't want to stem into just the walking verb, especially if the walker is played by Chuck Norris. It gets worse, because if you're stemming busy and business, which are two completely different words, or so they say me all the time, they get stemmed to something A, identical, which is wrong, B, which is not even a word, which is even more wrong. So starting with the most recent release, which have been in the cooking for a few months now, I guess, but is recently out, we have the true morphological library integrated into Sphinx, which does lemmatizing. And as opposed to stemming, which is basically a short and simple algorithm to identify the exact suffix that we want to cut, lemmatizers run off a dictionary, of a big enough dictionary of the language, and they either look up the specific word form in that dictionary and then replace it with a dictionary-based normal form precisely. So busy would get looked up in the dictionary, and it would get replaced by its original form, busy, ditto for business. And the funniest part, that even for the unknown words, lemmatizers behave much better than stemmers do, because in that case, instead of going with a few empirical rules, which often lead to mistakes in stemming, lemmatizers actually look at all the existing prefixes in their dictionaries, in their database of language keywords, and they identify a few best fitting rules to cut that prefix and transform even the unknown word to its normal form. Bottom line, lemmatizers are a little bit slower than stemmers. That doesn't matter at all when you're doing the searches themselves, by the way, because when you're doing the searches, you only have to lemmatize or stem a handful of keywords, and that happens instantly in a matter of a few nanoseconds, I guess, not even microseconds. They do have some additional impact on the indexing time, and that impact is anywhere in, say, 10 to 30% range according to my benchmarks. So what used to take a couple minutes is going to take a couple minutes and a half now, but they are much more precise than the stemmers are. So if you are serious about your, well, language issues, if you're serious about the search quality, then lemmatizers are definitely one of the biggest features in 2.2 to check out. So next slide. I guess. And yeah, this is the stemming problem number 2. The individual word forms that we index are sometimes ambiguous. So what exactly does this dove mean? We try to find the options on the next slide. So it might be describing someone diving, or it might be describing, well, someone flying, or it might mean a few it might mean a few more things, I guess. Here it's also a brand of some chocolates or something like that. Something I don't eat anymore. Next slide, please. So stemmers cannot really handle that, because all these stemmers can do for any language too. That's why I'm using the plural here. All that a stemmer can do, in this case, the English one, is to cut the prefix of word form, and that's it. Lemmatizers are a little bit more advanced. We also now have a mode which creates and which emits multiple different normal forms in case the original word form was ambiguous, like dove or left or something like that. And because we are now emitting more normal forms into the index size grows naturally, but it grows only by a small enough margin. My tests for Russian, which is more reflective than English and is supposedly worse in English in this regard. So on my tests on Russian, the index size growth resulting from switching from lemmatized underscore RU to the RU underscore all was just 15 to 20 or maybe 30% in the extreme cases, but that was about it. Guilty as charged, I didn't test it at all for the English language, but I would expect smallish enough growth in this case just as well. And why is this important again? Because now the situations in which you had an ambiguous word form, which you just can't handle using, well, plain old keywords or stemmers, these situations can now be handled. Any word form any word form will match any word form now, even though those keyword forms are ambiguous. That's it regarding the morphology. And coming up next, keyword expansion. And I'm actually going from the more sophisticated things to the simpler things, really. So morphology is kind of sophisticated under the hood, except that using it shouldn't be. There are maybe just 2 or 3 directives to simply turn the morphology on. From there, it kicks in, does the magic automatically. The keyword expansion in Sphinx that I wanted to talk about improves ranking a little bit. We have an automated method to expand every single keyword that you query for internally into the huge, or, well, not really huge, into the 3-way OR operator that you see on the slide. And doing this, expanding every single keyword to, well, the keyword itself, which would be stemmed or normalized via the lemmatizer, and then an infix, a substring, and then the keyword with the prepended equals sign, which means give me the exact form in Sphinx terms. Now, that simple trick well, not really kills the searching time, but definitely, let's put it mildly, definitely affects the searching time, but at the same time it increases the relevance a little bit, because this way we are searching for everything, but when we're matching a substring or the exact form, we know that more keywords matched and more important keywords matched, and the ranking formula can boost up the weights of such matches. That's about it. And of course, a punch in the MySQL ribs. I doubt there is a way to easily do that in MySQL. So next slide, and go into something even simpler than that, something foundational. Actually, and that's the general problem, if you will, of any full-text search system, specialized full-text search system compared to any database, really, not exactly limited to MySQL and Sphinx, which we currently dissect, is that, well, a database system naturally does not care that much about well, processing the text that it stores and works with. And there are a couple of seemingly simple questions, as in how do we even handle a simple punctuation sign? How do we handle those dots and ampersand signs and the question marks and dashes? How do we do that? So actually, if you start thinking about it really closely, if you will, it's a more sophisticated story than simply taking all the punctuation marks and replacing them with spaces. And the samples are on the slide again. In some cases, you want a dash to be to treat a dash as a space. In some case, you want to treat it as a word part. In some case, a dot is something in the middle of an acronym. In some other case, it's not only in the middle or end of an acronym, it actually delimits a sentence. It serves as a sentence delimiter, and coming up with a single simple empirical rule that would tell whether or not this dot is a sentence end or something in the middle of an acronym or something else is not as well. Is not trivial. You can't simply declare all the dots as your sentence ends, and you can't declare them as, well, just plain old spaces either. So sometimes, and this might be advanced functionality, but sometimes you want to handle that, because without handling those dots, you can't limit your sources to individual sentences or paragraphs, and without handling dashes and ampersands specifically, you can search for them if you need to. And we have a bunch of advanced features in Sphinx to handle those situations, blended characters that I will talk later, about later, and the index SP functionality to, well, analyze the dots and paragraph boundaries and store those into the index that I will not talk about anymore. But the bottom line of this slide is that, well, even something seemingly simple, such as handling punctuation, is not that simple really when you get down to it, and your search system has to help, and Sphinx does, and I don't think MySQL does. And next slide, to something fundamental. Now to something fundamental. The character sets. Curiously enough, the what is a character question is not a trivial one either, because in English we can't even type in those fancy versions of N with all the accents. So for us, well, technically I have a keyboard that can handle some Russian, but believe me, we don't have those accented letters in our language either. But that's not the case in French. Curiously enough, even if that N with a hat is a proper character which should be differentiated from a mere N in one language like French, this could be not the case in the other language like Spanish. Unfortunately, I'm constantly forgetting which language is which here. I do remember that in one of the language the difference can be dumped, the accent can be removed, and all the characters could be normalized to a plain old Latin N, and in the other language they are significant. The accents are significant. And I have no idea about French legalese. So curiously enough, again, even the simple SKI7 characters are not really safe from those conversions. So you can't simply assume that you could dump all the accents and get away with it. That really depends on the language. But moreover, there is at least one exception, the Turkish language, in which the plain old good SKI letter I case folds differently. Normally, the I with a dot would case fold to a big I, to a capital I without a dot. However, in Turkish, the normal lowercase I with a dot on top of it folds to a capital letter, to a special capital letter I with a dot on top of it, and vice versa. The capital letter I without a dot on top of it folds to something special in Turkish again. And then again, in Turkish, they don't consider some of the normal letters like W or Y regular characters too, so that adds to the confusion. The takeout even handling the characters, the individual characters and character sets is not so easy. Even something as fundamental as breaking down the text stream into individual words, sentences, paragraphs, zones, or anything else that you need searched, even that is not that simple. And unfortunately, most, if not all, database embedded search systems just do not care. So just to give you a quick overview of the Sphinx way, we'll let you define the character set table, which keeps track of all the known characters and lets you specify where do you want those characters mapped, and you can use that for case folding or accident removal. We're planning a bit of an improvement in that area, though, to make your guys' lives easier and introduce aliases for the most common languages and character sets in, well, in hopefully the nearest future. So that's it regarding the character sets. So we do not exactly mean grep when talking about the full-text search systems, as you can see. Something fundamental is more complicated than simply grepping. Something not so fundamental as, say, keyword expansions, ranking, perhaps combining the full-text search with additional attribute-based search, that's even more outside of the grep's scope, if there is even such a thing as grep scope. So full-text search is hard, and I guess we have a slide on that. And sometimes, occasionally profitable. I'm not sure whether or not Ryan sorted these the companies on this slide by their revenue volume, though. That's probably not the case, because Sphinx definitely makes much less than MySQL these days, and Xapian definitely, yes, Xapian definitely makes less than Google. I guess the awkward pause means that we want to see the next slide. So a brief comparison of Sphinx versus MySQL with regards to everything text capabilities related. So what can Sphinx do that MySQL naturally cannot? So we've got somewhat more advanced text processing capabilities. We've got stemming, we've got true morphology, lemmatizing, we've got a bunch of features, a bunch of more sophisticated features to help you with even more advanced text processing than that. We've got something to tweak and tune the handling of punctuations, delimiters for declaring different word forms, or even mapping idioms, multi-word forms to an individual word. We've got something to index in-document zones. Basically, think of XML elements. Something to add indexing exceptions, and so on. None of that is in MySQL, and this is curious too, by the way, because at least implementing stemming, well, everything that implementing stemming takes is, well, basically 10K, say 15K worth of C code, which they don't even have to write, which they simply need to borrow and integrate into their code. Unfortunately, they don't. So apparently, full-text search is not an area of focus for Oracle these days. Ranking is somewhat more advanced in Sphinx. Well, we focus on that, and MySQL doesn't. I figure that the only non-trivial ranking function that MySQL actually has, the one that they engage in the so-called natural language matching mode or something like that, if that one is roughly identical to our BM25 ranker, which is, well, simple, too simple for its own good. And last but not least, oh, I think there is a mistake on this slide. We probably should fix it for the published presentations. It says keyword expansion. It was supposed to say character set tables. So one more area of a difference when it comes to text processing is how we work with well, characters in the text. Sphinx basically lets you declare multiple classes of characters. This is a simple character. This is a so-called blended character. This is a character that I should totally ignore as opposed to replacing it with space. And this is a character, you get the idea. MySQL only has one character class, essentially. So in MySQL, it's either a character, or it's a non-character, or it's a delimiter. And the easiest way to define what is a character and what is not a character, the easiest way to customize that is to add your own collation into MySQL. If that doesn't sound easy to you, then keep in mind that the harder way is to, and the harder but still the officially recommended way would be to punch in your character set definition into MySQL source and rebuild MySQL. Not exactly convenient. So, well, bottom line, we suck at data storage. That's because we are a full-text search engine. But when it comes to full-text processing and sorting, we're a little bit better. Next.
I think this slide is me.
Yeah, so I'm biased. I can't deliver this slide.
We did promise to put together some benchmarking numbers, and to be fair, it's notoriously difficult to compare apples to apples when dealing with full-text search systems because no two systems have exactly the same configuration options, among other things. But what we've done here is do a simple queries per second benchmark of full-text searching in Sphinx, InnoDB, and MyISM. It was a small data set, only 4 million rows, and you can see that the hands-down winner here is Sphinx, which was able to process an order of magnitude more queries than InnoDB full-text searching. Actually, we did a bunch of benchmarks, but only one we got valid results because in the other ones, either InnoDB took more than an hour on a test, so it was killed, or MyISM took more than an hour on a test, so it was killed, and there was literally nothing to compare the Sphinx timing against, so we didn't include them here. Of course, this is a completely synthetic benchmark, and the specifics of how your application will perform will vary greatly based on the workload and data set, so don't take this as gospel, but just some quick numbers that we put together.
Yeah, especially, by the way, the InnoDB numbers, because, well, I think there should have been something wrong with our InnoDB, either InnoDB configuration or methodology in this case, but we couldn't find it. So naturally, we would expect that InnoDB at least performs at least as good as MyISM, but unfortunately, on our tests, it went the other way around.
And one of the interesting things that's not up here is we did testing on multiple versions of InnoDB, and I think it was 5.6 something beta, and then 5.6 something GA. So the InnoDB performance with the same configuration, just version differences, full-text searching was a factor of 10, right? So the more modern version of InnoDB full-text search was 10 times better than 5.6. Some early pre-release versions. So they are making great strides in InnoDB full-text search, but it's not where Sphinx is. So beyond performance, let's talk a little bit about scaling search. For anybody that's ever worked with MySQL, this diagram will look extraordinarily familiar. It depicts the standard approach of scaling out read operations by adding additional read-only replicas into the replication hierarchy. And because full-text indexing is now built in at the storage engine level for InnoDB, if you want to be able to scale searches, you simply do the same thing that you would do to scale any read operations, and that is just add more replicas. Some approaches are to dedicate a pool of slaves to serve only search queries, while others evenly distribute search queries among all the slaves in order to equally distribute the load. And neither approach is wrong. It really just depends on your workload and hot data set sizes. And there is, of course, only so far that you can scale given this particular approach, but honestly, it should get most applications pretty far before requiring significant architectural changes. And scaling MySQL search beyond this is really out of scope of this presentation, so let's move on to scaling Sphinx. In my opinion, scaling a system like Sphinx is much easier than scaling a system like MySQL. And here's the traditional approach to scaling Sphinx. Most organizations start out with a single instance of Sphinx, but then one of three things happen. Either the Sphinx data set becomes too big for a single host, or full-text search becomes so integral to the revenue stream of the application that it's no longer acceptable to be a single point of failure, or some combination of those two. And depending on why you choose to scale will dictate the approach that you take. The easiest approach that works for HA is to simply have multiple copies of your data. Here, the first diagram shows each node having a full copy of the data. So if any single node goes down, the HA proxy layer will simply take care of the traffic and will be redirected to the other two. The second approach works best for when your data will no longer fit on a single host. And multiple copies of the search index can be stored over multiple hosts so that both less disk is required and there's fault tolerance in the event of a single host failure. And there are a number of other approaches to scaling things when geographical distribution or redundancy is required. And we won't cover them here, but you can find them online with a quick Google search, or if you prefer, we can put together some links in a follow-up blog post. I think Andrew has one story specifically that he wanted to tell about how one fairly famous company scaled their Sphinx infrastructure to billions of documents, and I'll let him tell it now. Andrew?
Yeah, thanks. So when I saw these two slides with the typical MySQL cluster setups and the typical Sphinx cluster setups, my initial gut reaction was, oh look, this is Craigslist, because that's exactly what they did a while ago when migrating from MySQL to Sphinx. They initially had a farm of 20-something-ish, 25 maybe machines running MySQL slaves for reads. Unfortunately, those machines were maxed out all the time. The search quality wasn't great either, so they considered different search solutions to convert. But for them, the most active data set, the data set with all the currently running postings on Craigslist, is small enough to fit into a single machine. So they naturally converted to scheme number 1 with a bunch of replicas running under HA proxy. The only difference here being that instead of using 25 maxed out MySQL replicas, they were able to get down to either 8 or 10 machines tops running Sphinx at about 10% load on those machines. That was a while ago, so the exact numbers are most definitely off, but the orders of magnitude are not. So we were able to reduce the number of machines threefold or maybe as much as fourfold. At the same time, the load on those machines went down dramatically. So the replication scheme is still sort of the same. You copy all the data to all the hosts, except that it's easier to move around with a Sphinx, because instead of setting up replication in MySQL, you simply move around the files, and then you point an HA proxy on top of them. The other cluster setup with HA proxy over different shards, index shards on different machines, and well, the results being aggregated from the entire cluster, this is suitable to large operations. Our two favorite verticals here would be social data mining, with lots of data to mine through, and well, web search with, again, lots of data to search through. In that case, you need redundancy, you need the high level of sharding. The scheme on the bottom of the slide is probably the easiest, and at the same time the the most nicely working approach to go with. All right. Sorry, got carried away. And now on to something completely different, to search result quality, aka all the other knobs and handles that you can twist and tune to get better search result quality out of Sphinx. Surprisingly enough, this is not really limited to ranking. Next slide, please. So, and sometimes, most interestingly, sometimes it's not even about ranking per se. I mean, we frequently see different situations in which, well, changing the ranking formula, well, that does help a little bit. That does improve the quality metrics by a few percent, say 5, 10, maybe as much as 20%. But, well, semi-surprisingly, the biggest savings, the biggest improvements in the search result quality come from something else, not exactly tweaking the formula. And there is a bunch of stuff that you can and perhaps should do about it. Something should be done during the indexing time. The data that you search is only as good as the data that you index. So you've got to get your character set table right to, well, avoid simply missing certain keywords, especially the foreign ones. You might, if your searches frequently include special characters like dashes, ampersands, and so on, you might want to fine-tune the so-called blended characters. Finally, if your data contains a lot of different variations on, say, product model schemes, phone numbers, stuff like that, you might want to consider the regex-based filters to pre-process the data in the queries. Well, think about the product models, right? I should have probably put that on a slide, but I'll try to articulate. So there are approximately 7,400,000 different ways to write down a Samsung's laptop model which goes NB900X3C, and then it's a completely different machine from NB900X3A, just completely different. And in some other case, a difference in this last character doesn't matter. And most people would want to find that laptop using NB900 without a space, or with a space, or with a dash. And depending on the data source you are pulling your product listings from, it might be written really differently in those, well, data sources. So regex filters are not the panacea, of course, but they help you to deal with situations like that. But that's more, but they are more suited to the artificial things like product makes and models, phone numbers, stuff like that. When it comes to regular, well, keywords, regular words that actual people use, there are a few more features like word forms, exception, and morphology support that also needs to be enabled during the indexing time. And you probably won't get it right from the first attempt or even the second one. 2 or 3 attempts at different indexing time settings is typically what it typically takes. But once it's done, it's done. So everything indexing time, everything that needed to be applied at indexing time is applied now. You can proceed to actually tweaking your searches. And there are a few more tricks, actually less tricks than there are different indexing time directives to tweak, but still those are important. One, and by far the biggest mistake that we see in our consulting practice is when you don't do anything, when the user punches in a query with a lot of keywords, you run it in the default match me everything mode, the user naturally gets no matches. Users hate that. There's a simple trick with quorum which fixes that, and it's on the next slide, I think, or the slide after that. All right, so let's shuffle them around. So the quorum operator, instead of it basically relaxes the matching constraints, if you will, or in plain English again, I don't want to match, if the query is too complicated, I might not want to match every single keyword that the user asks for. I might add the limit of, say, 3 keywords per that query. Or alternatively, I could specify percentage. And again, there is a typo on the slides because 3.5 was supposed to read 0.35, which would in turn mean 35% of the keywords in this query. Because sometimes it's tough to set a fixed limit, a fixed keyword limit up front. And a couple more things that you should do to your search queries are, well, typo corrections, and I think keynote autocorrected Sphinx with a Y instead of I for us, because initially it was a Y. So apparently a cut and paste bug again. Well, the presentation got typo corrected, and unfortunately in this case this is not a demonstration of our correction tool, but our correction tool does exactly that type of a job too. We bundle it in the /misc/suggest folder in the root of the Sphinx source tarball. We probably bundle it with the binary packages too. But in any case, you can grab a source package and look at the MISC folder. So try it out. There is a simple 100-line PHP script which makes Sphinx do typo correction. Last but not least, in bi-language situation like the Russian versus English language player, a surprisingly big improvement in search result quality comes from detecting the mismatched keyboard layouts. So this example, I'm not sure if there is anyone Russian speaking in the audience, but in this example, a person tried to type something in Russian, failed a little, typed the first word with the English layout on, but the second word was all right. So autocorrections like this, they should be implemented in the application, and at this point, but surprisingly, they bump up the search result quality, well, a lot. So these are the tricks that you could do during the searching time. Now back to the previous slide with a little bit more on the indexing time magic that, well, Sphinx lets you implement. So the blended characters, which I mentioned a few times throughout this presentation. The magic characters, the magic blended characters are basically the characters that you're unsure about, that you're not sure how to index. Because when indexing brand names like AT&T, you probably do not want to drop the ampersand sign from the brand name. You want to be able to search for AT&T as a whole. While for the Procter & Gamble example, you probably want to drop that ampersand sign when indexing, but you don't know upfront. So blended characters do exactly that. Every character which you list as blended is going to be indexed twice, if you will. The baseline indexing, the baseline index will be built with all the magic characters replaced by spaces, but in addition to that, the tokens that mix and match normal and blended characters would be indexed too. And at the query time, the query positions will be adjusted so that the phrase and proximity queries would work just as expected, even though the characters are the magic characters were engaged and the keyword positions in the index are way off. So another thing that you can do during the indexing time is specify the exceptions for those one-off characters that you only want to index in a single individual keyword like C++. This is especially big on the job search sites, I think. C# and C++ are a major pain for them. They're easy with exceptions. And last but not least, there also are word forms which you cannot use for things like C++ with, well, actual pluses, because word forms, unlike exceptions, do not work with the raw text, with the raw indexed text. They work after the tokenizing and therefore case folding and the removal of the known characters have taken place. But the word forms can be used for well, actually many different things. Word forms can be, unfortunately we're missing the example again, but you can use them for mapping between different morphological forms of a word, or you could use them to map different synonyms of a word together, like map all the instances of tuna to fish, or map the keyword feline or feline. I'm sorry, I'm not sure how to say that. You could map that to, well, cat indexing time. So any search for a cat would also match all felines, and this is probably the most interesting application. The word forms could contain multiple forms. multiple words on their left side, meaning that you could map a sequence of words like core to do, that is a CPU modification, to something like C to D. So, and therefore use the word forms to, well, index either complicated EDMs or complicated multi-word keyword, multi-word product names or something like that. So they bear a bunch of different uses, both morphology and synonyms and whatnot. So that's indexing time. That was searching time. I guess we need to jump forward in time by a couple slides. And now to something yet different. So we've discussed a little bit how exactly a dedicated full-text search system is better than MySQL with regards to text processing. We've discussed a little bit how what can you do about the search quality, and there's quite a bunch of stuff to do during the indexing time and quite a bunch of stuff to do during the searching time, and we're not even scratching the tip of the iceberg when it comes to ranking. But what about the webinar title after all? It was supposed to be about configuring MySQL and Sphinx, right? And there are some really quick wins, which you could get by avoiding a few simple mistakes and or doing a few really simple improvements in your MySQL and Sphinx configuration. Unfortunately, I'm not really the MySQL expert here. I mean, I could hack it, add a patch to it or something like that, but I haven't got much MySQL DB experience, if you will, so maybe Ryan will add something. So the only suggestion here that I could come up with is to, well, drop the full text indexes to avoid constantly, once you switch to a different system, to avoid constantly updating them and clogging up MySQL with the full text indexing time.
Well,
now,
Andrew, if I can interject, one of the purposes of this slide was to sort of show that Sphinx has spent a lot of years sort of making itself configurable, and full text is really the focus. With MySQL, there's very, very little that can be done by the administrator or user to change the ranking, to change the indexing scheme or the performance time of indexing or search result timing, other than just standard sort of MySQL general tuning options, other than the handful of full text parameters. So in reality, you have very, very few ways to make MySQL return better full text search results, and that's sort of the point here of the story about Craigslist scaling from MySQL, MyEyes, and full text searching. The first thing they did was add replicas, and then they realized, well, that's sort of my only option at this point. Now we've maxed out our replicas. The only option after that is to use something that is not MySQL. So that's sort of the evolution. And you're right. The best quick win for scaling search in MySQL is to drop full text indexes and use a different solution. But I'll hand it back to you, Andrew.
Okay, so a bunch of different unrelated railway Sphinx tweaks. So what can you do about the indexing time if that part is slow? Well, first and foremost, you should check out your memory limit directive in the indexer. It maxes out at a little under 2 gigs for us because we've never been able to benchmark any difference between a 2 gig and a 4 gig memory limit setting. That is the only reason why. But the default values are, I think, set as low as 32 meg for previous versions and still something lowish like 128 megs for the more recent versions like 2.1 and 2.2. So if that's set to a default value or a way too low value, you want to tweak that. That'll improve your indexing time by a few percent or maybe even more than that if you're jumping from 32 meg to a gig on a big enough collection. Another interesting thing that you can do is to avoid joining data across tables that you pull the data from. when indexing MySQL data. So one approach would be one approach to indexing the data scattered across a couple different tables would be to use join and perhaps even group concat in your SQL query statement in Sphinx, which pulls the data from MySQL. The other approach would be to use joint fields. This is, not universal, if you will, but when it helps a lot. I've seen cases of 2x and perhaps even 3x indexing time improvement by, simply switching from joins on MySQL end to doing the joint fields on Sphinx end. Another interesting trick, and the following two are pretty low level too, well hidden in our source code and never advertised. So the two low-level tricks are as follows. First, if the IDs in your database are pretty sparse and the deltas between consecutive IDs are big enough, like 10 or 100 or even worse, 1,000, then you might want to try to generate the, Sphinx-only IDs as you index data, and you might want to use those IDs as your Sphinx IDs while storing the database-based IDs as your attribute. The thing is, we delta encode the Sphinx IDs internally in our data files, in our full-text index files. So when the IDs are dense and the deltas between them are small, the compression works better, and the resulting index size is somewhat smaller. It can be up to, 30 to 50% smaller in extreme cases, I would say. Another low-level optimization like that would be, and often overseen one, is to reorder the Sphinx fields, the Sphinx full-text fields when indexing your data, and put the biggest field, the biggest in terms of text content in that field, first in the list of the fields that you fetch from SQL. Again, this has to do with the compression scheme that you are currently using, basically, if you do that, then we use less bits to encode the positions in the most frequent field, but more bits to encode the positions in, the more rare full-text fields. And that saves on the index size again. So my testing collection is basically a block path collection with just a couple fields, title and content. If I index them as select ID and title and content, I get a 900 megabyte index. If I index them as select ID content title, if I put content first, and titles are short comparatively. So if I put them in that order, I get an 800 meg index. So that's a saving of 12% out of, thin air. And last but not least, indexing time. These first four things were all about performance, essentially, either improving the indexing performance or making the index smaller. The last bullet is about sacrificing it back, but improving on quality. So for indexing performance itself, try the memory limit, try the join fields. These are probably the two most frequent ones we are seeing. For index size improvements, quick wins here, try dense IDs and try reordering the fields. Finally, if you don't care that much, if you do care about your indexing performance and index size, but if you care about the search quality even more than that, then go ahead, check out word forms, exceptions, lemmatizers, blended characters, indexed zones, and all other fun stuff that we've touched before in this presentation.
All right, Andrew, I need to cut you off. We're about 5 minutes over, so we only have a couple of slides left. Some more quick wins, and then MySQL and Sphinx, and then questions. But since we're over the time limit, we're going to ask everybody to just post their questions into the questions in GoToWebinar, and then we'll answer them in follow-up blog posts, unless, Alyssa, you think we have time now?
Hi, Ryan. People, go ahead and put as many questions as you have. I'll keep the questions window open even after we close the webinar. I'll leave it open for a few minutes so that you can type things in. And then Ryan and Andrew will address all of those in a follow-up blog post. Does that answer your question, Ryan?
Yep, that sounds good to me. Andrew, is there anything you want to say before we end?
Well, that's a tough question, you know. I mean, I could go on for hours, but that can't happen. So most in the foremost, is that even right? Am I talking in English so far? All right. So actually, I wanted to thank everyone for coming and joining us, and sorry that I, well, exhausted the time limit, but be sure to ask any questions here or email them in later. You've got the credentials now. You've got the email addresses. Thanks, everyone.
Yeah, thank you, everyone.
Thank you, everybody. I will make sure that everyone gets a recording, a link to the recording and the slides sometime this afternoon. And also just wanted to remind you that the next Percona Live is April 1 through 4 in Santa Clara, California. And if you're interested in being a candidate for speaking, call for papers ends this Friday, the 22nd. So get those in, visit our website, and fill out the required form, and we'll hopefully see you there. Andrew, thank you so much for your time today. Ryan, great job as always. And like I said, I'm going to leave the window open for questions, so go ahead and keep asking them. And with that said, thank you everyone for joining us today, and I do apologize for us going long. Have a great day, afternoon, or morning. Thank you, everybody.